Welcome to The Explainer. Today, we're going to pull back the curtain on these incredible invisible engines that pretty much run our entire digital world. So, how does that even work? Well, the answers are hidden in two really powerful foundational ideas. These things have dominated tech for decades, and they each solved a completely different, really tough problem. So we're going to get to know the B+ tree. It's the real unsung hero behind basically every database you've ever used. And then we'll meet the LSTM, which was the breakthrough that finally gave AI something like a long-term memory. All right, let's jump right in with our first titan, the B+ tree. Now, this thing was built to solve one huge physical problem, and that is that disk drives are just painfully slow. Think about it like this. Getting data from memory, that's as fast as thinking a thought. But getting it from a disk? That's like having to physically get up, walk across the room to a massive filing cabinet, and then hunt for one single page. The entire point of the B+ tree is to make sure you have to take as few of those long walks as possible. Now, there's this subtle but absolutely crucial difference between the original B tree and the B++ tree that every modern database uses. You see, by putting all the actual data only at the very bottom level in what they call the leaf nodes, it means the B+ tree can cram its internal guidepost nodes way more tightly with just keys. And what does that do? It makes the whole tree shorter and wider. And that means, you guessed it, fewer of those slow walks to the filing cabinet to find what you're looking for. And this is the superpower, that linked list at the bottom. If you want to find, say, all your bank transactions from last week, the database just has to find the first one, and then it's like walking down a hallway, just opening every single door in order. It's this super fast, linear scan, instead of having to jump all over the place in the tree. But this process also shows us the B+ tree's big weakness, its Achilles heel. If you try to insert data using a totally random ID, like a UUID, you basically set off a performance nightmare. One tiny little write ends up forcing the database to read two different pages from that slow disk, split one of them, update the other one, and then write 3 whole pages back. It's just this cascade of slow, painful operations. Okay, so while the B+ tree was busy conquering the physical world of storage, a totally different battle was going on in the much more abstract world of AI. So let's switch gears and meet our second titan, the Long Short-Term Memory Network, or LSTM for short. And this thing was invented to solve a massive mathematical crisis that was basically grinding all AI progress to a halt. Yeah, just imagine you're trying to learn a new language, right? But by the time you get to the end of a long sentence, you've completely forgotten what the subject was at the beginning. That was the problem. Mathematically, the signal that tells the network how to learn was getting multiplied by a number smaller than 1 over and over again, with every single step it took back in time. And eventually, it just vanished. It became 0. The network was literally incapable of learning from things that happened more than a few steps ago. So the absolute genius of the LSTM is this one special thing, a memory line they call the cell state. The best way to think of it is like a conveyor belt. It just carries the important context straight through the whole network. And the key is, by default, stuff that gets on that belt stays on that belt, totally protected from everything else going on. And this memory conveyor belt isn't just running wild. It's managed by 3 really smart gatekeepers. And these gates, they're actually tiny little neural networks themselves. And their whole job is to learn what to do. They learn what old information to throw off the belt, what new stuff to let on, and which piece of information on the belt is the most important for making the very next prediction. This whole setup, this really elegant design, it basically created a super highway for that learning signal. It could finally travel all the way back through the network without just fading into nothing. The inventors had a great name for it, the constant error carousel. And that was the breakthrough. That was the solution that finally let AI learn from things that happened way in the past. So for years, it was like this. These two titans, the B+ tree and the LSTM, they just reigned supreme. They were the undisputed champs in their fields. But then, as always happens in tech, new challengers showed up. And they didn't just have small improvements. They came with completely different, totally revolutionary ideas. In the database world, you had the LSM tree, and it basically came along and shouted, "Hey, stop trying to modify data in place. All you're doing is causing slow, random disk access." The LSM philosophy was simple.
Never change anything. Instead, just treat every single change, even an update or a delete, as a brand new record you just stick on the end of a log. And just like that, you turn those slow, random writes into blazing fast, sequential ones. And over in the AI world, you had the transformer. It came from that famous paper, Attention is All You Need. And man, it just threw out the entire rulebook. It completely abandoned the LSTM's whole one word at a time sequential thing. Instead, it proposed something that sounded kind of crazy. Just look at all the words in a sentence at the exact same time, all at once. Okay, so here we are. We've got these two clashing philosophies, the old guard versus the new challengers. So let's actually see how this plays out. Let's compare them on the metrics that really, really matter. All right, in the database arena, the whole fight really boils down to this one concept called amplification. The best way to think about it is as the hidden cost of everything you do. It's the ratio of work the database actually does behind the scenes compared to the tiny bit of work you asked it to do. So, simple rule, low amplification is great. High amplification is really, really bad. And right away, you can see the problem. B+ trees? They have terrible write amplification. Remember that tiny little update we talked about? It forces a huge 16 kilobyte page on the disk to be completely rewritten. But LSM trees, since they're just tacking things onto the end of a log, they keep their write amplification incredibly low. This is amazing for anything with tons of writes, like a social media feed, where thousands of new posts are hitting it every single second. But there's always a trade-off, right? The LSM tree pays a heavy price with high read amplification. To find just one single piece of data, the database might have to look in memory and then check a bunch of different files on the disk just to piece together what the current value is. The B+ tree, though, with its predictable 3 or 4 disk seeks, it is still the king of reads. And that's exactly why it's perfect for something like a banking transaction, where you absolutely have to find one specific account balance, like right now. Now, over in the AI showdown, the transformer's absolute killer feature was how perfectly it aligned with modern hardware. See, an LSTM is stuck being sequential. You simply cannot calculate step 100 until you finish step 99. But a transformer? It's really just a series of gigantic matrix multiplications. And that is exactly what GPUs are built for, doing that kind of math in a massively parallel way. Honestly, this is the reason we've had the recent AI boom. So, after all that, who wins? Well, the surprising answer, and I think the most interesting one, is that this whole battle isn't about finding a single winner at all. It's about creating this rich, diverse ecosystem of specialists. The future is this idea called polyglot persistence. It sounds kind of fancy, but all it really means is using the right tool for the right job. Smart engineers today, they don't try to use one database for everything. No way. They'll use a B+ tree for those critical banking transactions because reads have to be fast and the data has to be perfect. They'll use an LSM tree for logging data from millions of IoT sensors because that's just a constant fire hose of writes. And then for big data analytics, they use something totally different, like a columnar store that's built to scan huge columns of data, not tiny individual rows. And get this, the original Titans aren't just rolling over and giving up. Not at all. The B+ tree is being totally re-engineered for these new ultra-fast NVMe drives, which gets rid of some of its old weaknesses. And the guy who originally invented the LSTM, he recently came out with something called XLSTM, a brand new version that's designed to be parallelizable, a direct shot at the transformer's biggest advantage. So this constant cycle of innovation, it really leaves us with one final thought. The Titans that we have today, they were built on ideas that challenged the way things were done back then. And as our hardware just keeps getting faster and crazier, creating brand new possibilities but also new problems, it makes you wonder, right? What new idea, what new philosophy is being cooked up in some lab or some garage right now that's going to become the next Titan of tomorrow?